Welcome. This lecture is about functions, which are also known as static methods, and in fact in the Java world you will more often hear people talk about static methods than about functions. There's a strategic choice for any course teaching Java about in what order to introduce the two kinds of methods that Java provides. In Java, as I said before, systems are structured as collections of objects, and objects can exchange messages. And when an object receives a message, the behaviour that it will carry out as a reaction to that message is normally encoded in a piece of code which is called an instance method. And it's possible to introduce those first in a Java course. However, I think this course takes the alternative approach of introducing static methods first, principally because we're talking mostly to people who have already done a course in Haskell, and Haskell functions are most closely related to static methods, so this seems like the easiest way in for you. But you should bear in mind that the kind of methods we're talking about here are actually the less common of the two kinds of methods that you will have been introduced to by the end of this course. The key difference, perhaps, is that because an instance method is encoding what an individual object will do when it receives a message, the code that records that instance method has access to all of the data that is contained within that object, and will have an effect on that particular object. And this gives you a slightly different code structure and a different way of thinking about it. Whereas static methods have none of those complications. They are very much like Haskell functions. You can think of them as being black boxes that take some data in and do some stuff to it and return you a value. Why do we want them in the first place? Well, let's consider a program, and the idea is that this program helps children to save their pocket money towards a target. And here is a version of the program that does not use any functions apart from that one obligatory public static void main that you've seen in every Java program that we've had so far. So let's have a quick look at it. You can see that the code is structured as two very similar chunks. So at the top we are describing a boy whose first name is Jock and whose second name is McInnes, and we are calculating the string boy name, which is done by putting together the first name and the second name, and he has some weekly pocket money and a savings target, and we can calculate how many weeks he has to save by dividing the target by the weekly pocket money, and then we can print out the result. And then in the second chunk of code we do very, very similar stuff for a different child, using some slightly different numbers. Okay, well, that's all very well, but it's a lot of code to do not very much. It's not very easy to read, and if something changes that affects both the boy and the girl, we've now got to change it in two places. So that's all a bit of a pain. So let's see what we can do instead. Here is the kind of output that we're expecting from this program, and that's not going to change as we rewrite the program. We're going to be doing a thing called refactoring, which is to say we're going to change the design of the code without changing its functionality. So lots of duplicate code. And in steps, what we're going to do is we're gradually going to reduce the amount of duplication by spotting it and replacing duplicated code by two different calls to the same function. Okay, so the very first thing we've done here is we've invented a new function, we've extracted a new function called join names, and this is going to take two strings which are going to represent the first name and the second name of somebody, and it's going to do the putting together of those names with a space separating them. And we replace the string addition that we had before by calls to this function. And so, for example, looking at the string boy name equals join names Jock McInnes line, what that does is it says, well, this is an assignment to a string boy name, So in order to work out what the new value for the string boy name has to be, we have to evaluate the right-hand side, just like we would have evaluated the right-hand side when it was Jock plus space plus McInnes. But in this case what we do is we evaluate the result of calling the function join names on the arguments Jock and McInnes. And then inside the function the same thing is done. The return value is put there in place of the function call, just the same way that the result of joining those two strings would have been put there in place of the actual expression describing how the strings were put together. And the same function is called in two different places. We can keep going. Here's another new function extracted to replace another piece of duplicated code, and again we replace the duplicated code by calls to the function. And we see here we have two identical function calls there, except that they're being given two different arguments. And again we extract a new function for printing how many weeks to save. That goes to print the results. It takes as argument the name and the target that we've previously calculated by calls to our earlier functions. So what did we do there, and why was it beneficial? So there are a number of different benefits to breaking down a program into functions, and in order to realise these benefits it's important that you give your functions good names, and by a good name we mean a name that actually accurately describes what the function is going to do with its arguments. This helps you to keep your thoughts straight. It helps you to do the decomposition of a complex programming task into simpler steps. It helps to hide the implementation details from the callers of a function. Now you might not immediately see why that's beneficial, especially when you are both the person writing the function and the person writing the code that's going to call the function, as we were right then. But we'll see some examples in a moment of how that can be helpful. For now, let's just say it is useful in that when you are reading some code that calls a well-named function, you may well be able to avoid the work of actually reading the code that the function carries out. You may just be able to say, well, maybe it's enough for my purposes to assume that the function called join names does what I would naively expect of a function that is called join names, namely I expect it to join the names. And sometimes you can get away with that, and that's great, and you've saved work. Sometimes you can't, and you have to go and read the code of the function, but at least then you're no worse off than you would have been if the code of the function had been pasted there into the program in place of the function call, as it was in our original version of the Pocket Money program. The other benefit is that if the person who is in control of the code of the function is a different person from the person who's actually writing the code that calls the function, we get the extra benefit that the implementation details of the function can change without the code controlled by the person calling the function having to change at all. Of course, this requires a certain amount of trust. You have to know that the changes are beneficial, that we're not going to be sabotaging the client code there. Where we came in was with the most obvious motivation, which is to say reduce duplication of code within a program. Nobody likes writing the same thing more than once, and so there are various slogans capturing this in the software engineering world. Write once is a very general rule that basically says you should try to embody each decision in the code of a program just once, and of course as soon as you've got duplicated code you have the decision about exactly what that code should be embodied twice in the code of the program, which opens you up to possibilities like when you change it you accidentally change one and you fail to change the other, which is a rich source of bugs. So another slogan that means exactly the same thing really is that you should write dry code. In other words, don't repeat yourself. The least important reason here is that it enables reuse of code across multiple programs. I say the least important because people often overestimate how important code reuse is to writing good, well-modularized code. The reason is that actually, in practice, enabling somebody to reuse a piece of code across multiple programs is not that easy and involves a lot of work other than writing the code. It, for example, requires decent documentation and maintenance plans and testing plans and what have you. And in many circumstances, it's actually easier to just rewrite the program. Exceptions being, of course, in specialised situations such as you are starting to become familiar now, where you are writing in a language where there's a very well established and well maintained library of existing code that you can use, confident that somebody is managing all of that maintenance of that code and documentation and so on. You wouldn't dream, I hope, of writing your own replacement for math.random, for example. You just are very happy that somebody else has written a function for you to be able to get a random number, and you just use it. Okay, so I'm wittering a little bit here. Let's get a move on. The high-level motivation of all this is readability and maintainability. And we're not talking about readability of the code because somebody would like a nice bedtime story of reading your code, although there's no accounting for tastes. The main idea here is that if your code is readable, that makes it easier to get it right. And maintainability is strongly related to readability. This is about handling the situations in which what your code must do changes in future, either because the requirements change or because something about the technical environment changes. And that in turn requires being able to read it in order to understand what it did in the past and what it should do in the future. And so that helps you to keep the code right in future. And so this is what it's all about. We're about making your life as programmers easier by making it easier for you to get your code right and to keep it right in future. So don't regard this stuff as being kind of esoteric requirements from the Inf1B team. Regard it as being a set of suggestions for how you can learn to make your life easier by developing good habits of doing this kind of thing. So that might be seeming a bit airy-fairy. Concrete advice: whenever you can clearly separate tasks within programs, and we'll see some more examples as we go on through this lecture, you should do so. And by the way, this is already a useful thing to do, even if you're talking about writing a function which will only be called once. And the reason is because you get the benefits of decomposing a complex task into simpler steps, even if one of your steps is only used once, and you get many of the benefits of hiding implementation details and so on, even for a function which is only called once. But of course, if your function is called many times, you get even more benefit. You should aim for methods to be no more than about 10 to 15 lines of Java. Shorter is absolutely fine. Longer is getting a bit dubious in design terms. If you have a method that's more than about 15 lines, it's probably a sign that it would be better designed if you split it up. So always bear that in mind. A function should do only one thing, and that thing well. If somebody asks you what your function does and you say, well, it does blah, blah, and then it does blah, and then it does blah, then probably that's a sign that actually you ought to have a high-level view of what it does, and perhaps there ought to be 3 separate functions that are called within your function. Okay. So let's see an example of how it's easier to change code once it's broken down into functions. So what have we changed here? What we've done here is, somewhat artificially, we've got a bunch of modifications to the functionality of the join names function, for example, where we are putting in the calculation of a title. Incidentally, it's a title that only applies to somebody of one particular first name, which is why I say it's rather artificial, but you can imagine better examples, I think. And the point is that the way that's actually called doesn't have to change at all, only a small aspect of the functionality of that function join names has changed. And similarly, you know, perhaps there's some special allowance in the pocket money for sweeties and you want to encode that and so on. Or maybe you want to have a row of asterisks in your print weeks to save. You have one place, you know where to look to make that modification. There's no choice about where to look. Your modified version is still a fair description of what needs to be done in order to carry out the functionality suggested by the name of the function, and the client code, the code that's actually calling the functions, didn't need to change at all. So that's what I just said. Makes it easier to localize modifications. So now let's look at a different example. We're going to now calculate the Euclidean distance between 2 points. So the kind of problem we're addressing is, suppose we have some kind of special point P, which we're usually going to think about as being the centre of a group of points. How close are various other points to P? So we're going to be looking for the closest point to P. Oops, there's a typo, trying, not tiring. We're going to use the Euclidean distance, and we're going to do it in the 2D case. So as I'm sure you're very well aware, if we use Cartesian coordinates so that P is P0, P1 on the x and y axes respectively, then the distance between 2 points represented in such a way is the square root of the sum of the squares of the differences coordinate-wise between them by Pythagoras. So here is a function that can calculate the distance between 2 points given using their x and y coordinates. So now we're going to pause for a moment and go into a bit more detail about the anatomy of a Java function, as much as anything else, to get some terminology settled. So what have we got here? Public static, you've seen before in the context of the main method. These are sometimes called modifiers. It's not a terribly important term. Public just means that any code anywhere is able to call this function, and for the time being all our functions will be public, although you'll meet private functions later. Static indicates that this is the kind of method which isn't being called on one particular object. It's just doing the kind of black box job of taking in some arguments, performing some calculation and returning the result. There's a return type next. So our distance function is going to have a return type which is double, which is to say that the type of the thing returned from any call of this function is going to be double. So when you evaluate the context in which this function can be called, the context should be one in which a double is expected, because after the function's been called, the result is going to be a double, and so that should fit into whatever expression it's going to be placed next to. For example, if we were going to go double x equals the result of calling the distance function, that would be fine. If we were going to go string s equals the result of calling the distance function, that wouldn't work. It would give you a compilation error. We always have a method name, which, as I've mentioned, I think it should be a well-chosen name to describe what the function does. In this case we've got distance. Then we have a bunch of parameters, and parameters have types, which can be any types within the Java language. There's a list of them. They're separated by commas. They're surrounded by round brackets. You've seen this in the context of the main method already. We have a body enclosed by curly brackets as usual. Then we write our Java code inside. What else is there to say? There has to be a return statement if the function returns a value at all, and that's preceded by the special keyword return, as you can see there. You can have local variables within a function, and I think we'll have more to say later on about what that actually means, but the point there is that variables which are declared within the body of a function like this are just for use within the function. There's no possibility that they're going to get confused with any variables outside the function, even if those have the same names. That's often very handy, because it means you don't have to negotiate who's going to use which names across your team of hundreds of software developers. And the whole thing is the declaration of a function. It's actually a definition of the function as well, but there you go. When you call a function, we already saw examples of this, you can either do so using literal arguments, as in the top line, or you can do so using variable arguments. That's not going to surprise you. You've already seen in other contexts that variables can replace literals in other contexts in Java, such as when we used an integer variable to specify how long an array we wanted, for example. So, suppose inside our class point distance we're going to define a function distance with some code as we saw before. Then inside our main method, which we still must always have, we can call it. And we'd do it something like that. We would say that our double dist is going to be equal to the result of calling the distance function on those arguments P0, P1, Q0, Q1. So functions are providing a new way to control the flow of execution. You've already seen for loops, while loops, and so on. So when the function is called, control transfers to the code in the body of the function. And the parameter variables are assigned the values given in the call. So like if we give 3.0 as the actual parameter, we sometimes say, to a particular call of a function, then the formal parameter, we sometimes say, in the definition of the function is given that value 3.0, which can then be used in the function code, which is executed next. Then the return value is assigned in the place of the function call in the calling code, and control transfers back to the calling code, and so we go on. You might think that's very obvious, but we've already got some interesting design decisions in the space of programming languages going on here. So Java uses what's called call by value or pass by value. So parameter variables are assigned the values that are given by the arguments to the call, and these are copied. You should think of them as being copied. The function doesn't have access to the, if you like, the actual variable. It can't change the variable in a way which will be seen by the calling code after the function has returned. It just has access to the value of the argument. We'll see an example in a moment. But the key point is that if you receive an argument and then you change it within your function body, then the change that you make to it within your function body does not have any effect on the calling code. The only way for a function to have an effect on the calling code is to return a value which is then used by the calling code. And this is a good thing because it means that it's easy to understand what's going on when you call a function. And there are some small amounts of lies going on here, which you'll see shortly. But here is a classic example of what we mean. Suppose we've got our add1 class here with our add1 method, and this is going to receive an integer which it's going to refer to as num as a parameter, and then it's going to increment it. Okay, so it's going to replace num by num plus 1. And because it's a void function, it doesn't have to have a return statement. It doesn't have to return anything at all, and indeed it doesn't. When it is invoked from the main function, we do so in a context like this. We're saying we have an integer x, which we initially set to 0, and then we call the add1 function, which indeed does take a copy of that x, which is 0, and add 1 to it. So within the called code, add1, the value of num after that num plus plus line has been carried out is indeed 1, but then that value is thrown away. Okay? So when control returns to main and we system out println x, x is not 1 but 0. Okay, it has not been modified. The fact that a copy of x was incremented and turned into 1 during the course of our calling of the add1 function is completely irrelevant to the original variable x within the main function. It makes no difference at all. And so we get 0 printed. And here is a picture of the same thing. I don't think I'm going to labour this anymore, but you can see what it's doing. We're saying we are copying the value of x into num, and we increment num, not x. Another piece of terminology, and this one it's worth knowing about because it sometimes gets misused, and therefore you may need to be aware of whether you're encountering the strictly correct use of the term signature or the common misuse of it, because you'll come across both. So strictly speaking, the signature of a Java function consists of its name and its parameter list. So that's the number of parameters and the types of the parameters, and order matters. Okay. So here's an example signature, max taking two integers, int x and int y. That's the signature of a Java function. But what people will often do is refer to the whole head of the function definition, the whole line, public static int max, int x, int y, as being the signature. Okay? Strictly speaking, that's the head of the definition of a function. That's just a tiny piece of terminology that you just need to know. So the return type of a function is stated in the header of the function declaration. We've seen that already. And we've just seen an example of a function declared void, which means it doesn't return a value. If it has a non-void return type, then it has to contain a statement of the form return and then something or other. Can be an expression, can be a single value, but the important point is that that return value, whether it's an expression or just a value, must evaluate to something that matches the type that the function is supposed to return. So here is an example. What do we want to say about this one? We've got an add function here. It's going to take two integers a and b. It's going to add them up and assign the result to the variable result. Now, that int result inside the function add, it's a local variable. Okay, that int result variable is not accessible anywhere else. However, the return statement returns the value of the integer value variable to the calling code. So again, it gets copied. So when we look at how this function is called within the main function, we start off setting our integer c to 0, and then we say we're going to give a new value of integer c, which is going to be the result of adding 3 and 2. So 3 and 2 are copied into a and b respectively. Result becomes 5 as a result of the code in the add function, and then that integer 5 is copied back to the main function and becomes the new value of integer c, okay, which we then print out, and that gives you what you expect. And here's a picture of that too. Now, that was all very nice and simple. Unfortunately, some types in Java, and array types are the ones we've mentioned, and you'll shortly find out that objects have exactly the same things applying to them, are what's called reference types. And that means things work a bit differently. Now, it isn't actually really any different. What's going on is that when we talk about arrays in Java, the variable that we use as the name of an array is really the name of a reference to some actual storage. And that reference is the thing that's being passed by value, not the storage itself. So you've got shallow copying going on, if you like. So when we copy the name of the array into a function, we make a new copy of a pointer to the place in memory where the actual data is stored, but we don't make a copy of the data. Okay. And that's why when you pass an array into a function, you can change the elements of the array, although you cannot change, the array itself, like its length and its type and so on. And so the effect of this is that if you pass arrays into a functions, you can kind of get side effects. So you can find that the calling code can be affected by the fact that some of the elements of an array have been changed, and not just by what the calling code chooses to do with any result function, any result value from the function. So here's an example. So what have we got here? We've now got an add1 function returning void, so no return value at all here, but it takes an integer array this time. And what does it do? It looks at the 0th element of that array and it increments that. Now we're going to call that function by saying we're going to first set ourselves up with an array called A, which contains the elements 0 and 1, and then we're going to pass that array to our add1 function. Okay, and then we're going to print out the contents. And what we will find is that the 0th element of that array, which happens to have the value 0, has indeed been incremented in a way that we can see in the calling function in main. Why? Because when we called add1, that reference A to the array was copied, so now there's a new reference to the array which is in use inside add1, and indeed there's a new name as well. It's now known as an array inside the add1 function. But the actual contents of the array were not copied. We just had now, if you like, two different pieces of string, two different pointers pointing at the same piece of memory. So that can take some getting used to, but once you've written a few functions in the labs, you'll be quite happy with that, I'm sure. And here's a picture of that. And yes, so here is a picture of the fact that we've actually got two different references to the same chunk of memory essentially. And that's all for now.